I'm going to go through question 1 from the 2018 AP Chemistry exam. Now the first question here is talking about this equation where we have Na2S2O3 sodium thiosulfate plus NaOCl turns in plus 2 NaOHs turns into 2 Na2SO4s plus 4 NaCl and H2O liquid. It says a student performs an experiment to determine the value of the enthalpy change delta H of reaction, and I would say watch out for that one, delta H of reaction, for the oxidation-reduction reaction represented by the balanced equation above. So first thing it says determine the oxidation number of chlorine in NaOCl. So we can do that. What happens is we have a couple of ways to look at this problem. One, we know NaOCl is really Na plus and OCl minus, and we know that any ion, its oxidation number is the same as the charge on that ion. So we'd say the oxidation number here is plus 1, and for OCl we can treat it as a little algebra problem. Oxygen in its compounds is almost always minus 2, and chlorine, let's call that X. And when we put those together, it's going to give us the charge of the ions. We'll call that minus 1. So minus 2 plus X equals minus 1. So we know that X is going to be plus 1. So that is the oxidation number of the chlorine in NaOCl. Another way to look at that is to look at the electron configuration of OCl minus. And oxygen has 6 valence electrons, chlorine has 7 valence electrons, and because it has a minus charge, that means we have 1 more electron. So we have 6 plus 7 plus 1, that would be 14 electrons. And so we would start is give everybody an octet, and that's 2, 4, 6, 8, 10, 12, 14. So that is the right expression right there. That's the picture, that's the Lewis dot structure. So we'd go back next and say, okay, oxidation number is the charge an atom would have if we assigned any shared electrons, so these two, to the more electronegative atom. So oxygen is more electronegative than almost everything. It's the second most electronegative atom, only fluorine is more electronegative. So oxygen is going to get that pair of electrons. So the oxidation number of oxygen is going to be 6, its normal valence electrons, minus the 8 it has right now. So that gives us a negative 2. Chlorine normally has 7, but in this case it has 2, 4, 6. So that gives us an oxidation number of plus 1. So back here when we said that oxygen in its compounds is almost always minus 2, it's because in a bond, oxygen is almost always the more electronegative atom. When is it not? When it bonds with itself, like in peroxide, or when it bonds with fluorine, which is the only more electronegative atom. Anyway, the answer here for chlorine is plus 1, and that is worth 1 point in this problem. So we have 1 out of 10 so far. Okay, the second part says calculate the number of grams of sodium thiosulfate needed to prepare 100 milliliters of a 0.500 molar solution of Na2S2O3. So first off, we're going to need to have the molar mass of Na2S2O3. So using the numbers from the periodic table on the test, I see that sodium is 22.99. I'm going to multiply that by 2. The sulfur is 32.06, multiply that by 2, and the oxygen is given as 16.00 multiplied by that 3, and I get 158.10 grams per mole. Now for part B here, we go on, so we start with 100 milliliters. Then we're going to go from milliliters to moles. That's our molarity. We're using the molarity as a conversion factor. And then we're going to go from moles to grams. We use our molar mass as a conversion factor. And we end up with 7.90 grams of sodium thiosulfate, and that's worth 1 point to get to the answer. And if you at least got to this point where you figured out how many moles of the sodium thiosulfate there was, that is worth 1 point. So part B is worth 2 points. If you got all the way to here, that's worth 2 points. But if you didn't have that answer, then they would go back and look, did you at least use your volume times molarity and get to moles. You didn't have to stop at moles, but that's a point, 1 point if you didn't get all the way to here. Okay, for part C, in this experiment, the student uses the solutions in the table below. So here is our 3 reactants. And those 3 reactants we're using 0.5 molar solutions in 5 milliliters. So hopefully we notice is that if we multiply volume times molarity, that we're going to get the same number of moles in each case. Okay, so using the balanced equation for the redox reaction and the information in the table, determine which reactant is the limiting reactant. So we can go back and say, well, we need 1 mole of this, we need 4 moles of this, we need 2 moles of this. So this one is going to get used up faster, and since they're the same moles in all 3 cases, then the sodium hypochlorite is going to be the reaction that gets used up first. The reactant that gets used up first. And that's for 1 point for stating that answer and giving a reason. For example, all 3 of these have the same number of moles. You need 4 of these compared to 2 and 1, and so that's going to get used up first. That'll be your limiting reactant. That's 1 point for the answer with the explanation. For part D, we start off with a graph. So all the solutions originally at 20 degrees are combined in an insulated calorimeter. The temperature of the reaction mixture is monitored and as shown in the graph below. So according to the graph, what is the temperature change of the reaction mixture? Well, we have to read the graph and say, well, this line is 32, this is 34, so that means this is 33. So halfway between about 32.5 degrees Celsius. And this one is pretty easy to see, that's 20.0 degrees Celsius. So whenever we do a delta, okay, it's always final minus initial. So it's 32.5 minus 20. So that's going to give us the answer here of 12.5 degrees. So final minus initial, the delta T is 12.5 degrees, and that's worth 1 point for getting this point. Now the next one, E, says the mass of the reaction mixture inside the calorimeter is 15.21 grams. So we're given a mass, and we're talking a calorimeter. Okay, calculate the magnitude of the heat energy in joules that is released during the reaction. Assume that the specific heat is 3.94 joules per gram degree, and that the heat absorbed by the calorimeter is negligible. So we're saying, make this an easy problem, and hopefully we can see what this is a Q equals MC delta T problem, because we're asking for the heat, we're given the mass, we're given the specific heat, and we just figured out the delta T, in the other part. So we're just going to substitute these in. So the 15.21 grams, they told us in the problem, 3.94 joules per gram degree, they told us in the problem, and the 12.5 that we got up in the part above. So we multiply those together, we get 749 joules, okay, and that is worth 1 point to get to that point. If you had some funny answer here for your graph, as long as you use that answer, you would get full credit on this part E. Now, using the balanced equation for the oxidation-reduction reaction and your answer in part C, calculate the value of the enthalpy change of the reaction. Now, this is an interesting one. So the delta H reaction in kilojoules per mole of reaction. So we have to watch out for that one. Include the appropriate algebraic sign with your answer. Now, that's also important. So we're saying here that energy is released. So we said 749 joules, that's just how much energy released. If we are releasing energy from the reaction, that's going to be a negative delta H. So negative delta H means energy reaction. So when we get all finished with our answer, we got to be sure and put a negative sign in there. So keep that in mind. Now delta H is the heat divided by the moles of the reaction. So delta H is heat divided by moles of reaction. So we've got that heat, that's the 749 joules, and we need moles of reaction, but we need to do that in kilojoules. So first off, let's get our moles. We know the limiting reactant was sodium hypochlorite, so let's figure out the moles. Back from the chart, we said 5 milliliters, and it was a 0.5 molar solution, which is 0.5 moles of NaOCl per 1,000 milliliters of NaOCl. So we get 0.00250 moles of NaOCl. But that is not this moles, okay? That's the moles of the chemical, But we had to go back and look at the reaction, and it takes 4 moles of NaOCl in order to get 1 mole of the reaction as written. So when we say moles of reaction, we mean for this guy as written. Okay, so we're going to say if I had 0.0025 moles of NaOCl, I got to say it takes 4 moles to get 1 mole of reaction. So the moles of reaction is 0.000625 moles. So if they saw that you took that number here and got to the moles of reaction, that's worth 1 point. Then all you have to do is take our energy, the 749 joules, divide by the moles. It asks for kilojoules, so we've got to say, kilojoule, joules to kilojoules, and this negative sign. So once you do all this, we get negative 1.20 times 10 to the 3 kilojoules per mole of reaction, and you get a point for getting that negative sign. So the 2 points on this part of the problem are for getting to the correct moles and for including the negative sign. So if a really common mistake here was to use this number of moles, okay, then you didn't get that point because you didn't change it to moles of reaction. But if you at least had the negative sign, you got 1 of the 2 points. If you forgot both, then you're kind of in trouble. Okay, the last part. The student repeats the experiment, but this time they double the volume of each of the reactants. So the old chart was 0.5, 0.5, 0.5, and 555 milliliters. So here we have 10 milliliters. And so we said that delta H is the energy per mole. Well, if you double all this, we're going to get twice as much energy, but we're also going to have twice the number of moles. So if we have twice the energy and twice the number of moles, we're going to get the same result. So that's what it is asking here in F. The magnitude of your delta H when you double everything turns out to be the same. So explain this result. And so you're doubling the heat, but you're also doubling the moles, and that's why this does not change. That's worth 1 point for that explanation. Last part here is write the balanced net ionic equation for the given reaction. So this is the reaction way back from the beginning. And so we say it's Na2S2O3. That breaks up to be 2 Na pluses and an S2O3. 4 NaOCls, that's 4 Na pluses and 4 OCl minuses. NaOH, 2 Na pluses, 2 OH minuses. And on the other side of the arrow, we're going to have 2 times 2. We get 4 Na pluses and 2 sulfates. And we get 4 NaCls. That's going to be 4 Na pluses and 4 Cl minuses. And we have an H2O liquid. So all of the other ones are aqueous, H2O is liquid. So we're going to knock out our spectators. And the only spectator we have here is sodium. So we have 2 sodiums. We have 4 more sodiums. We have 2 more. So we have 8 sodiums on that side. Here we have 4 and 4. We have 8 sodiums on that side. And when we take those out, here's our equation. That's our net ionic equation. And writing that is worth 1 point. Now this is something that kids across the nation did not get correct. A lot of people missed this up. And even when I did it, I made one tiny little mistake and just had to be really careful. But that, is just worth 1 point just for knocking out all your spectator ions. So be sure and practice how to write net ionic equations. So this is a 10-point problem. Okay, we've listed all the numbers there, and that is question 1 from the 2018 AP exam.